Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Homework, Lecture 106. Problem 1. Show that the Clausius-Mazzatti relation can be re-expressed as this. Okay. That's fairly straightforward exercise in just algebra. Set this off to the side. Number 1. All right, so we start with kappa minus 1 is equal to n alpha over epsilon naught minus n alpha over 3. Okay, which we can take this denominator and just multiply it on the left, and we'll get kappa minus 1 times epsilon naught minus n alpha over 3 equals n alpha, for which we can then distribute the kappa minus 1. So we'll just write kappa minus 1 times epsilon naught minus kappa minus 1 n alpha over 3 equals n alpha, like this. And so we'll just collect the like terms, the n alphas. We'll get kappa minus 1 epsilon naught equals n alpha plus kappa minus 1 n alpha over 3. Let's factor out an n alpha over 3 on the right hand side here. So that'll give me n alpha over 3. Now, we need a 3 here, because n alpha over 3 times 3 will give me the n alpha back. But here, we'll just have kappa minus 1. Adding 3 and minus 1, we get n alpha over 3 times kappa plus 2. And now we can solve for n alpha. Or, excuse me, we can solve for alpha. So alpha equals 3 epsilon naught over n times kappa minus 1 over kappa plus 2. And that is it. Pretty good. All right, number 2. Show that the Clausius-Mazzatti relation shown in problem 1 reduces to kappa equals 1 plus n alpha for a gas. Use helium from lecture 105 as the basis of your calculation. Okay, so number 2. So remember, the expression that we're considering, right, is this expression that kappa equals 1 plus epsilon naught n alpha over epsilon naught minus n alpha over 3. So that's our starting point. And from problem, what number was it? Well, no, from the lecture in lecture 105, right, we were given that for helium anyways, we had that kappa was equal to 1.0000, I don't know if zeros? Yeah, 5. Which means that in alpha, right, because in that lecture it said that kappa was equal to 1 plus in alpha. So that means that in alpha, of course, is just equal to 0.00005. Well, if that's the case, then the denominator here, epsilon naught minus n alpha over 3, is going to be equal to, well, epsilon naught is a huge number. It's 9 times 10 to the 9. So 9 times 10 to the 9 minus a really small number divided by 3, right? This is approximately still just equal to epsilon naught. Well, if that's the case, right, then kappa will be equal to 1 plus epsilon naught in alpha divided by epsilon naught, which is just equal to 1 plus n alpha. And so you can see that in the case of a gas where n alpha is a very small number, our Clausius-Mazzatti relation becomes the same simple relationship for the dielectric constant that we got with our simple model in lecture 105. All right, problem number 3. Use the Clausius-Mazzotti relation to calculate the polarizability of nitrogen and its atomic radius. Assume that we use the usual density for gases, the 22.4 liters per mole. Look up the dielectric constant for nitrogen. However, assume it is for N2 molecule and have the polarizability in your calculations. That's just a hint, and I'll show you what I mean by that as we get into it. Let's see here. Number 3. Okay, so according to Google's AI, the dielectric constant for nitrogen is 1.00058. So I will assume that this is for N2 at the nitrogen molecule at standard temperature and pressure. From the lecture we have that alpha, so N2, is going to be equal to 4 pi epsilon naught times the atomic radius R naught cubed. So I would then say that for just a single nitrogen atom, I'm going to have this value and write it as 2 pi epsilon naught R naught cubed. So now let's use the Clausius-Mazzotti relation from the lecture. Alpha sub n is going to be equal to 1/2 3 epsilon naught, again I'm having, over n times kappa minus 1 divided by kappa plus 2. So I halved it just like I did the actual value up here. Well, I didn't have the value up here. I'm having the value of this so we can get nitrogen atom, not molecule. Yeah, so now I'm going to plug in for kappa is equal to 1.00058. So we'll get 1/2 times 3 times 9 times 10 to the 9th. And that's farads per meter, but we'll just ignore the units. Divided by n, which I pointed out was 2.7 times 10 to the 25. That's inverse meter cubed. And then all multiplied times, well, 1.00058 minus 1 is just going to be 0.00058. And 2 plus that value will just be 3.00058 in the denominator here. Plug that into the calculator. We should get that this is 9.6 times 10 to the minus 20, and the units, of course, are coulomb meter squared per volt. Now, I hope that's right. I made some weird error with the exponent in an earlier calculation I was doing for the class, and I'm not sure why I made the error, but I'm pretty sure this one's right. So 10 to the minus 20. All right, so that's the part A of the problem, I guess. That's to calculate the molecular polarizability of atomic nitrogen. Now let's calculate the radius of a nitrogen atom. So we would write that the radius, and we're going to use this formula up here, the 2 pi epsilon naught R naught cubed. So R naught is just going to be equal to the cube root of 3 over 2 pi n times kappa minus 1 over kappa plus 1. And so this is just 1/2 alpha. So this is the value that we got up here. So if we plug that in and we take the cube root of that, so it's really just the cube root of this value we got before, the 9.6 times 10 to the minus 20, then we will get that this is 1.5 angstroms. I seem to recall that I don't think we got 1.5. I think we got 1.2. I don't want to punch it into the calculator again, but I think that's the value that I get when I calculate that. The true value is I think 1.5 angstroms for the radius of a nitrogen atom, well, calculated by some other method. But anyways, that's what we would get for the radius of a nitrogen atom. All right, number 4. This is the barium titanate problem. So one point of confusion that I might just address right at the beginning when solving problems like this. Let's think about just a square. And I want to have basically a grid of squares. So there's a neighboring square over here. And then there will be neighboring squares all around this. And if I put, say, an atom at the vertices of these squares, then there really is only one atom per square. You can see that we have 4 atoms that border this, that are kind of in the square, but each of these atoms is shared by its neighbors, right? So we only get 1/4 of the atom here, because there would be a square up here, of course, and then up here, so you got 1, 2, 3, 4. So it only shares 1/4 of each atom. But since we have 4 atoms on the boundary, that's 1 atom per square. So we have the same kind of thing going on here with barium titanate, where the oxygens, which are red, are face-centered, right? And so they're going to be half in the unit cell. And so that'll come into our calculation when we get into it in just a minute. All right, so part A, calculate the net dipole moment in a unit cell of barium titanate. Assume the oxygens are half in the unit cell. That's kind of what I just said. All right, so part A. So the dipole moment, little p, it's just going to be the sum of all of the charges times their separation, right? That's just the dipole moment of each of them. So we'll do them one at a time. First, we'll deal with the 2 oxygens at the top and the bottom, right? If you look at the top face and the bottom face, you see those oxygens up there. So we have 2 oxygens, and they're both half in. Their charge is -2, I'll just write electron charge units. And if we look at the displacement in the diagram here, this is a slice, right? A slice. And we see that they're displaced by -0.009 nanometers. So -0.009 nanometers. Okay, then we're going to have the 4 oxygens going around the other 4 faces. So now I'm going this face, and then the front face, and then the side face, and then the back face. We have 4 oxygens. So I'll add 4 oxygens. Also half in, and the charge on those is -2 electrons. And this time, however, the separation, if we look at the picture, we see that these are only separated by 0.006 nanometers. That's the displacement. And finally, we have the titanium atom at the center of the unit cell. And for that, we don't. It's not fractional. It's the whole titanium is in the middle of the unit cell. So we'll just have, all right, +1 times 1, because the whole thing's in there. The charge, however, is +4 electrons. And its displacement, if we look at the picture there, it's also 0.006 nanometers. And if we add that all up, we're going to get basically 0.066. Now we have to take and then times the electron charge times, and this is in nanometers. So let's get it in meters and also put the charge back in. So we'll have 1.6 times 10 to the -19 coulombs for the charge, and 1 times 10 to the -9 meters, because this is in nanometers. And that gives us a value of 1.057, I'll call it, times 10 to the -29 coulomb meters. So that's part A. Part B asks us to calculate the unit cell volume. And for that, the dimensions in the 3-dimensional representation here, the 0.398 nanometers and 0.403 nanometers tall. So it's just a simple volume formula for a cube, right? So the volume is just 0.398 times 10 to the -9 meters, and that'll be squared. And then the height of this cube is 0.403 times 10 to the -9 meters. And we get a volume of 6.38 times 10 to the minus 29 cubic meters. All right, and then part C is to calculate the polarization of barium titanate. So for that, we just use the two parts, A and B, that we just did, because the polarization, big P, sorry about that in the last lecture, I couldn't remember the term polarization for some reason. I kept calling it like dipole moment per unit volume, which is accurate, but it's easier to say polarization. Polarization, big P, is equal to the dipole moment, little p, divided by the volume, or the number of dipoles per unit volume. And that will be equal to, we just divide part A, which is the 1.057 times 10 to the minus 39 coulomb meters, by part B, the dipole volume, which is 6.38 times 10 to the minus 29 cubic meters. And we get 0.166, we'll call it, coulombs per meter squared.